Okay, so welcome to this class on Shannon's theory. So as I told you in my previous classes that Shannon's theory is a very fundamental theory in the art or science of cryptology. So essentially it was the seminal paper in 1948 and 49 which essentially postulated certain theories. Okay, so they essentially form a cornerstone of what we know as today's ciphers. Okay, so if you will find that whatever basic formulations or basic properties we find in today's ciphers, you can essentially go back and find that those things existed in an old paper in 1948 and 49. Okay, so we will try to understand some of the concepts in those papers. So in today's class the objectives will be as follows. So we will try to understand the definition of what is meant by perfect secrecy, okay, and prove that a given crypto system is perfectly secured. So that is our objective, that is a given crypto system, we should be able to essentially find out whether it is perfectly secured or not. Okay, and then we will see that how to construct or realize certain kind of perfectly secure ciphers. So we call them one-time pads or OTPs. Okay, so after that we will go into a very fundamental instrument that we use for our these kind of proofs. So it is called entropy. So we will try to understand what is entropy and its computations. Okay, and then we will follow that up with the definition of ideal ciphers and conclude with a topic called equivocation of keys. Okay, so I will gradually progress and we will try to understand these concepts. Okay, but these concepts form a part of Shannon's theory and we will actually conclude with something, but maybe not in today's class. Okay, so first of all, what I would like to define what is meant by unconditional security. Okay, so essentially the idea is that we are essentially considering an adversary who is powerful. Powerful enough means who has got unbounded computational power. So the idea is that given a cipher and given an adversary who has got unbounded computational power, then whether he or she is able to break a given crypto system. Okay, so that means when we talk about unconditional security, it concerns the security of crypto systems when the adversary has unbounded computational power. So unbounded computational power means it has got infinite resources. Okay, so infinite resources means what? It has got infinite time, it has got infinite space, and the question is whether even then whether it can break a given crypto system. So what do we mean when we say break a crypto system? Obtain the value of the key, right? So essentially we have seen various kinds of attacks, we have seen like various classes of attacks. So we will be considering that, we will considering a ciphertext only attack. That means the adversary has got access to only the ciphertext. Okay, and given an unbounded computational power, whether the adversary is able to ascertain the value of the key. Okay, so the question obviously which comes to our mind is, when is a given cipher unconditionally secured? Okay, so in order to understand that, we will use some theory of probability and we will try to understand how what is the model of an unconditional adversary, and is an unbounded adversary, and try to understand what is the definition of unconditional security. We also call that perfect security. Okay.
So when we are considering the ciphertext only attack, we already know that algorithm.
Yeah, that is the basically we have, as we have said, that the Karskov's principle essentially said that the algorithm is open, right? So the security lies only in the value of the key. So the value of the key is not known to the adversary. So the adversary knows the algorithm, everybody knows the algorithm is in the public domain. Okay, so what you don't know is the value of the key, and the question is whether you can ascertain the value of the key, right? So therefore we will use certain terms in probability. I call them as a priori probability and a posteriori probability. Okay, so the idea is as follows. So whatever encryption you consider, it's basically a function, right? It's a function from the domain of a plain text to ciphertext. Okay, so therefore as we have seen in our old classical ciphers, they essentially comprised of what? They considered, for example, let us consider just the alphabets making up the plain text, right? So therefore how many possible letters or symbols are there? There are 26 letters or symbols. Okay, so these 26 letters or symbols are being somehow transformed and converted into a ciphertext, right? So therefore all of these letters like A, B, C, D, so on to Z has got some probabilities, right? As we have said, like in English language, E is the most frequently occurring letter, right? So therefore, they have got some probability distribution initially before the ciphertext starts, right? And that is what we call as the a priori probability, right? And that is getting essentially, so therefore we denote by the term ppx. So as if you can see here, we denote by the term ppx a priori probability of a plain text, okay, and therefore this is the probability that is assigned to every letter or symbol of the plain text before the encryption has started, okay. So essentially the key also has got a probability distribution, and therefore now when the encryption function takes place, okay, so therefore what happens is that the plain text gets converted into the ciphertext. So if we consider a crypto system where the plain text and the ciphertext both comprise of say English letters, then the initial frequency or probability distribution of the plain text is getting transformed into a different probability, right? So therefore there is a probability transformation, right? So therefore let us consider, like for example, by as we have said that ppx denotes the a priori probability of the plain text, right? Similarly, we have got pkk, which denotes the a priori probability of the key, right? So the ciphertext is generated by applying the encryption function. So therefore, if we consider that the plain text by x, or denote the plain text by x, and there is an encryption function say e, okay, and based upon the value of the key, we know that x is getting transformed into y, okay. So what we note out here is that both the probability distributions, that is the plain text and the key, are independent, right? Because when we are choosing the key, in general we do not think about what is the value of the plain text, right? So therefore the two distributions, that is the plain text distribution and the key distribution, they are independent, okay. This observation is actually very important, so please commit to your memory that the plain text distribution and the key distributions are independent. We will use that in our future calculations, okay. Then we obtain the ciphertext by applying the value of the plain text and also the chosen value of the key, and we obtain a ciphertext probability distribution, okay. So now what the attacker wants to do is that it wants to compute the a posteriori probability of the plain text. So the idea is as follows, okay. Before going into the complications, the idea is as follows. So the idea is like this, that is, when you obtain the ciphertext, what you do is that you have got certain values of the symbols, right? So what you do is that you guess the value of the key and then you try to decrypt the ciphertext, okay. I mean, so the moment you decrypt the ciphertext, what you obtain is the plain text, right? So this plain text, right, what you obtain, this also has got a distribution, right, and that is called the a posteriori probability, okay. Now if your a posteriori probability matches with your a priori probability, then probably our guess of the key was correct, right? But if you obtain, for example, like if your guess is wrong, then maybe when you go back, then the plain text that you obtain does not make any sense, okay. So let us, I mean, if you are not really clear, we can make it clear by the example of maybe a shift cipher, okay. So consider a shift cipher. So in shift cipher, what did we do? Every letter was transformed by some other letter, right? So for example, it could be a shift, right? Maybe a fixed shift or maybe not a fixed shift, but we had basically done some transformations, right? So therefore, for example, there is a legible or rather a meaningful English language text. Consider a paragraph of meaningful English language, okay. So when we apply shift cipher, it gets transformed into another set of alphabets which essentially does not make any sense, right? So what did we do for our cryptanalysis? We essentially guessed the value of the key and then decrypted back, right? So when we decrypt back, what we can do is that we can check what is the original plain text, right? That is our objective also, right? So when we go back, we guess the value of the key, we go back and obtain the plain text, right? So now this plain text or this paragraph that we obtain, which is probably the plain text, has got a probability distribution, right? But that is actually based upon the value of the key, right? After the ciphering, after the value of the ciphertext, that is, given the value of the ciphertext, what is the probability distribution of the corresponding plain text? So this probability distribution is defined as the a posteriori probability. Now if your guess of the key was correct for a shift cipher, then that paragraph would have definitely made a sense, right? It would have been a meaningful text. Nobody encrypts a meaningless text, right? That is the basic assumption. So if somebody encrypts a meaningless text, then I'm really not bothered, right? So therefore, the idea is that if that makes sense, that means essentially the probability distribution that we obtain in the corresponding text should essentially match with our normal English language, right? So therefore, in that case, my a posteriori probability matches with the a priori probability, right? And if that is so, then the value of the key is correct, right? So do you understand the idea behind this? So therefore, there is a definite idea why Shannon postulated this, right? So therefore, essentially it tries to explain mathematically what we did for our cryptanalysis, right?
Adversary has access to the probability distribution of the plain text.
Yeah. For example, English language plain text, all of us know, right? So the adversary also has a fair amount of idea of that, right? So the idea has an access to that. I mean, the adversary has an access to that as well. It has also access to the encryption function. Okay. So I'm repeating this because it should go into our mind, right? So for example, now consider that the probability distribution on P and K induce a probability therefore this we have understood, right, that the probability distributions on P and K, that is the plain text and the K, induce a probability distribution on C, which is the ciphertext, right? And what is the ciphertext? We can denote as follows, like for a given K, CKX is equal to EKX, where X belongs to the corresponding plain text, right? So this is simple. So the question is that, so this is a fundamental question, does the ciphertext leak information about the plain text? Right. So therefore, given the ciphertext Y, now what we shall do is that we shall compute the a posteriori probability of the plain text. Okay, we denote that by PPX given Y. So you understand this. So what is this symbol called? This is conditional probability, right? So therefore, we apply the principles of conditional probability and we can actually compute this value, right? So PPX given Y and see whether it matches with that of the a priori probability of the plain text, right? So if this matches with the a priori probability of the plain text, then probably my key is correct, right? So therefore, if we would have wanted a proper amount of security, or what we would say as a perfect security, then we can actually denote this as follows. We would have written like PPX given Y, okay, that is equal to PPX. So what does it mean? So this is the basic idea of a perfect secrecy or perfect security. What does it mean? Yes? Okay. Okay, so therefore, I really don't know what to do. So the idea is that, I don't know why this is not shown there. Okay, so let's continue. I will try. I mean, what I am trying to say to you is that PPX given Y is equal to PPX. Okay, so therefore, probably I had written out here somewhere. So PPX given Y is equal to PPX. Okay, so which means that for all X given Y belongs to P, and for all Y which belongs to C, okay, this result holds. That is, a crypto system has got perfect secrecy if this is the case. Okay, and what does it mean? It means that essentially given the value of Y, okay, the probability distribution of X is indistinguishable from the probability distribution of X when you are not given any value of Y. So which means what? Which means that the ciphertext Y is not giving you any additional information, right? So you see that slowly we are trying to understand the meaning of information, right, or the meaning of uncertainty. So information and uncertainty are quite related, right? So we are trying to see how those things are formally described, mathematically described. Okay. Yeah. You have not understood. Okay, so therefore see. So what I am trying to say is that suppose consider a simple shift cipher and consider that this is the probability distribution of X. Okay, so that is I have described by PPX. That is a normal English language description, right? So now you consider that you have done a shift cipher. So which means what? You have got a y ciphertext. So now I am saying to you that given this distribution of y, whether the now what you can do is that you can guess the value of the key and obtain back the plain text, right? So that is nothing but, so the probability distribution now that you obtain is ppx given y. So if these two things, so that is what I was trying to say, if these two things match, right, then essentially it means that this y is not giving you any extra information, because even then it is still the same, right? So it's not giving you any additional information, right? So let's talk, let's I think get, I think this will get clear with the help of an example. So therefore let's see one example. So therefore consider this is a crypto system. This is just a sort of a diagrammatic representation of a crypto system. So you see that this is a very simple transformation which says that your plain text comprises of the letters A and B, okay, and your ciphertext comprises of the letters or symbols 1, 2, 3 and 4, okay. So what is the transformation? The transformation says that you can start with A, and if your k is k1, then you go to 1. If your k is k2, then you go to 2, okay. If your k is k3, you go to 3, right. Similarly, the other transformations. So what you see is that if your plain text is B, then also you get some other mappings like 2, 3 and 4, okay. So therefore this is the corresponding mapping that we are concerned with. So now let us try to understand certain things about what we have just described, okay. So for example, consider that your plain text which forms the set of P equal to AB, okay, has got a probability distribution. So which means your A has a probability distribution, your B has a probability distribution, right. So it essentially follows a probability distribution, right. So therefore A has a probability of occurring and B also has a probability of occurring. So what is the probability of occurring of A? It is say 1 by 4. So this is given, okay. So what is the probability of occurrence of B? It is 3 by 4. Note that, of course, I mean the probability of occurrence of A plus the probability of occurrence of B is equal to unity. Okay, so this is obvious because A and B are the only possible texts, right, text symbols. So what is the value of K? The K could be K1, K2 and probably K3 also. Okay, so this is a mistake here. So therefore, so consider that suppose there is a key called K1 and the probability distribution of K1 is half, okay, and the probability distribution of K, the probability of occurrence of K2 and K3 are same. So what is that? It is equal to 1 by 4, okay. So what is the ciphertext? Ciphertext is 1, 2, 3 and 4. So now the question is, what is the a posteriori probabilities of the plain text given the ciphertexts from C? So which means that you have been provided the corresponding ciphertext, and the question is, what is the a posteriori probability of the plain text? So which means what is the probability of occurrence of say A or B once you have been given say the ciphertext is 1 or 2 or maybe 3 or 4, okay. So we will consider one such case. Now this encryption function is often represented by this table also, okay. So you see that A is the plain text, K1 is the key, then your ciphertext is 1. Similarly, you can also check other such mappings, okay. Is this clear? So I will keep this figure and I will try to compute the value of the a posteriori probability as follows, okay. So therefore, first of all let us try to understand what is the probability that 1 occurs at the ciphertext. So what is that probability? So you see that 1 could have occurred only from A in this mapping, right. So that means we would like to multiply, because as I have already told you that the plain text distribution and the key distribution are independent distributions, okay. So in order to obtain the probability of 1, we can simply multiply the probability that A occurrence of A multiplied with the probability of the key K1, okay. So what is the probability of A? It is equal to 1 by 4 and the probability of occurrence of K1 is half. So we multiply 1 by 4 with half and obtain 1 by 8, right. So that is the probability of occurrence of 1. Similarly, we can also obtain the probability of occurrence of 3, right. It is slightly more complicated because 3 can occur from A as well as B, okay. But in this case you see that this A and this B are two exclusive cases, right. So therefore we can apply the theory of or theorem of total probability, and what we can do is that we can multiply the probability of occurrence of A with the probability of occurrence of K3 and add that with the probability of occurrence of B multiplied with the probability of occurrence of K2, right. So this is simple, right? So what we can do is that we can just simply multiply 1 by 4 with 1 by 4, add that with the product of 3 by 4 and 1 by 4, and this works to 1 by 4, right? So this is actually 1 by 16 plus 3 by 16, okay, not 1 by 1. So it is equal to 1 by 4. So likewise I can also compute the other probabilities, right? So you see that we can obtain the probability of the ciphertexts, right, as follows. But our question is what? Our question is to find out the a posteriori probability, which means, say given the ciphertext is 2, I would like to compute what is the probability of occurrence of A, right? So this is quite simple, right? So if I say you, for example, that the ciphertext is 1 and ask you what is the probability of occurrence of B, what is the answer? It is 0. You can easily compute. So you see that, does it match with the probability of occurrence of B? No. So which means that this is not a perfect cipher, right? So this is a simple check. But we will try to compute a little bit complex situation, which says that what is the a posteriori probability of A given that ciphertext is 2. Okay, we will just try to understand this complicated thing, although we have easily understood that this is not a perfect cipher. Why? Because we have to essentially go to the generalization, right? So generalizations are always complex equations. So in order to understand that, it's interesting to work with a simple example. Okay, so let us consider this. For example, that suppose your PPA given 1 is 1 and your PPB given 1 is 0, right? So this we have already understood, I guess, right? That is, if your plain text is 1, your ciphertext can be A, and that occurrence probability is actually 1. And if your plain text is 1, then the occurrence of B as a plain text is actually 0. Okay, so you would like to compute this also. That is, what is the a posteriori probability that A occurs as a plain text given 2 as a ciphertext. Okay, so you know that this 2 can actually come from 2 plain text. It can come from A as well as it can come from B. Okay, so the 2 can come when the plain text was A and the key was K2, or when the plain text was B and the key was K1. Okay, so now the question is, given 2, we need to compute the probability that it came from A, right? So is it that of choosing K2? Is the probability same as that of choosing K2? No, because we see that there are other mappings where K2 has been chosen where 2 is not the result, right? For example, this one. You see this mapping, the K2 is chosen, but actually I have ended up with 3 as a ciphertext, right? So it is not equal to that of choosing of the K2, right? So therefore, how do we compute that? So therefore, let us see. I mean, for example, these 2 can appear with a probability as which we can work out as follows, by having A as a plain text and K2 as the key, right? So therefore, A is a corresponding plain text and K2 is the value of the key. So what is the probability? So we know that we can multiply the probability of the plain text and the key because they are independent. So it is the product of 1 by 4 and 1 by 4, and it works to 1 by 16. You understand that? Because the probability of occurrence of A is 1 by 4 and K2 as the key is also 1 by 4. So you multiply them, it is 1 by 16. Okay. The other case could be by having B as the plain text, okay, and K1 as the key. You see that? The other chance could be that B was the plain text and K1 was the key, right? Because K1 is chosen. So what is the probability of occurrence of B? It is 3 by 4. And what is the probability of occurrence of K1? It is half. So we multiply them and we obtain 6 by 16. So what is the total probability that 2 can occur? It is 7 by 16, right? So we have basically broken up the possibilities into 2 cases, right? So what is our desirable case now? Our desirable case is that 2 has occurred as a ciphertext and it has occurred from A. So which is the first event. You see that by having A as a plain text and K2 as the key, what we have done is that we have obtained 2 from the plain text A. And that is precisely what we want, right? We want what is the probability distribution of A given that 2 is your ciphertext. Okay. So what we do is that we divide 1 by 16 by 7 by 16 and we obtain the value of 1 by 7. Right. So I guess you understand that we can now generalize this also. Like consider any set of plain text and any corresponding set of ciphertext and any set of keys, of course. So we would like to generalize this idea of a posteriori probability. Okay. And this we can do by the help of this equation. Okay. So do you understand this equation? So you see that what it says is as follows. So it basically tries to compute the value of ppx given y. So this is what exactly we are doing in our toy example, right? So the denominator is all possible ways how you can actually obtain y, because y is the ciphertext. Okay, so you remember in the previous case what did we do? We essentially took that corresponding ciphertext and decrypted them by all possible values of the key and went back to the corresponding plain text, right, and then multiplied with the probability of that plain text. Okay, so you see what I'm saying? What I'm saying is that in order to compute this total probability, that is of occurrence of 2, what we did is that we took, for example, any key, like for example choose k1, okay, and decrypted this 2 with k1, went back to the corresponding plain text and multiplied with the probability of the plain text. Okay, and again choose k2, multiply, obviously the probability of k2, and then decrypt it and go back to a and multiply with the probability of a, right? Similarly, we can do it for all possible keys, right? So that is exactly done here. So in this case, you see that you take the corresponding ciphertext y, you decrypt them by all possible keys, multiply with the probability of the corresponding plain text, and of course multiply with the probability of the key, right? And then do a sigma over all possible such keys, right? And your interesting case is the fact that your x has occurred as the plain text, and you essentially multiply them with all possible keys, which essentially takes you from the value of x to the value of y, right? So essentially so therefore this is exactly what we have seen in the previous example. Okay, is this generalization clear to us? Yes. Okay, so therefore, so now essentially we know how to compute the value of ppx given y, and we essentially I think I've already defined, but given you the idea, but this is the formal definition. It says that a crypto system has got perfect secrecy if the value of ppx given y is equal to the value of ppx for all x given belongs to p and for all y belongs to c. Now the value of ppx we already know. We can engage this previous equation to calculate the value of ppx given y, because you see that on the right hand side everything is known to us. We know the value of the key, we know the value of the the probability distribution of the plain text as well as the plain text the probability distribution of the key, and therefore we can use this equation, okay, because we also know the mapping, that is we know the decryption function. So we can use this formula to calculate the value of ppx given y, okay, and check whether this value of ppx given y matches with the probability of ppx. If ppx given y matches with ppx, then we have got perfect security. Okay, so that is the idea. So that informally it means that a posteriori probability that the plain text is x given that y, the ciphertext y is observed, is identical to the a priori probability that the plain text is x. Okay, so that is the definition of perfect security. Okay, so let's see when some examples where we can have perfect secrecy. Okay, so consider a simple example of a shift cipher. So in a shift cipher, what we did in our what we have seen in our little bit not so simple shift cipher, if you remember, we have taken a and we have mapped them to any of the possible outputs, right? So there are 26 possibilities for the first letter. The second letter b maps to any of the symbols except what a has been transformed to. So there were 25 such possibilities. So if we keep on multiplying in such a fashion, then the size of the key is equal to 26 factorial. We have seen that, right? So what we will try to see here is that if each possible mapping is chosen randomly, then shift cipher achieves perfect secrecy. Okay, so we will try to use our previous formulation and we will try to establish this fact. Okay, so suppose the 26 keys in the shift cipher are used with equal probability. So what means that? That means that each plain text, each key, occurrence of each key has got a probability of 1 by 26, right? So then for any plain text distribution, the shift cipher has got perfect secrecy. So which means that actually we are not bothered also what is the plain text distribution, okay, and we can still achieve perfect secrecy, right? So do you see how? So you see that your P, K and C can be said to form the set Z26. Okay, so Z26 we have seen that it's a set of integers from 0 to 25, right? So your k, therefore you immediately understand, lies between 0 and 25, and your function is very simple. It is just x plus k mod 26. So idea is that if for each symbol of the plain text, if you choose the value of the key at random, that is any mapping you can just choose, okay, arbitrarily, then essentially, and if you obtain the corresponding value of the ciphertext, okay, so then the question is whether this gives you perfect secrecy, right? So which means that when you choose, so it means you should try to understand this fact that what we are saying is not such a scenario in which for all the plain text we are using the same key. It means that for each symbol, okay, that is each symbol which you want to transmit secretly, you have to essentially choose the value of the key also at random, right? So for example, there is a letter like say abracadabra, and if you have to encrypt say A, B, C, like so on, then for A you have to choose the corresponding key at random, for B also you have to choose the key at random, for C also you have to choose the key at random, okay. So it doesn't mean that for the entire plain text we are using the same key, right? So for each symbol we are choosing a value of key at random. So what do you see is the practical implication? The practical implication is, you see the practical problem? The practical problem is that for each symbol you are choosing a key at random. So in order to decrypt also you require the same key, right? So you immediately understand that you have to transmit lots of keys, okay, and it's actually in this case the same as the number of the plain text that you want to transmit, right? So if you know how to transmit the key secretly, right, then why not do the same for the plain text also, right? So even though you obtain a perfect secrecy, a notion of perfect secrecy, but that is not practical, right? So we'll try to first establish why it is a perfectly secured cipher, and later on go into another case where we actually obtain a perfect secrecy. It's called a one-time pad, and then talk about its practical problems, okay. So this is the mathematical formulation. It says that ppx given y, we have already seen this, is equal to ppx multiplied with pcy given x divided by pcy, okay. It is the same thing as what we have seen in the previous equation, right? So it is the denominator is the probability that y has occurred as a ciphertext, and the numerator says that x has occurred as a plain text, and that has been multiplied with the probability that y has occurred given x is a plain text, right? So can you understand what is the value of this pcy given x? It is the same as the probability that the key has been chosen, and that key is equal to y minus x mod 26, right? So you see that when we had computed the value of ppx given y, that was not equal to the value of the probability of the key. We discussed that, right? But in this case it's equal, because if you choose the value of the key to be y minus x, and if your plain text is x, then obviously your ciphertext is y, right? So therefore this probability you can denote by these symbols. It says that you can actually multiply with the corresponding value of the key, okay. So you see that pcy given x is equal to the value that is equal to the probability that, I mean, you have to basically choose the fact that the key is equal to y minus x mod 26. What is the probability that the key is equal to y minus x mod 26? And what is the probability? That is 1 by 26, because we have assumed that each key is being chosen at random, right? Similarly, we obtain the value of the corresponding value of the y occurring as a ciphertext. So what is the probability that y occurs as a ciphertext? So you choose all possible keys and you decrypt your y, okay, by using your decryption function. Multiply that with the corresponding value of the key being chosen, right? So what is the value of the key? 1 by 26, okay, and what is the value, what is dky, this is some probability, right? So you can keep it pp y minus k, but when you take the sigma, 1 by 26 comes out, and you have got a summation over probabilities. So what is that equal to? It's equal to 1. So you have got 1 by 26. So now you see that the result is established, because pcy given x cancels with pcy. Both of them are equal to 1 by 26, right? So if these two things cancel, then you have got ppx given y is equal to ppx. So what does it mean? You have got perfect secrecy. Why? and because your a posteriori probability of x given the value of y matches with your a priori probability of x, right. So if we can do this for shift cipher, we can do it for any given cipher. We can basically what we have to do is that we have to compute these values of probabilities and try to see whether we get a match, right. So this was just a very simple example. Okay, so you can, if you see your Stinson's book, there are several exercises given, and I will also give you one as an exercise. So you can just practice, and if you can do it for one, probably you can do it for the others as well. Okay. So basically now let's try to think of a theorem, or let us try to establish a theorem. It says that any encryption function, okay, which you can, or any crypto system essentially can be denoted by a 5 tuple, right. You have got P, C, K. So what is that? Plain text, ciphertext, and the key, and your encryption function and your decryption function, right. If these 5 things are defined, then you have defined a crypto system, right. So let us consider the case that the size of the K, size of the C, and the size of the plain text are all the same. That is, your cardinality of your key and your cardinality of the ciphertext and cardinality of the plain text are the same. Okay. So the crypto system offers perfect secrecy if and only if every key is used with probability of 1 by modulo k. Okay. So in your previous example, there were how many keys? There were 26 keys, and the occurrence of each key was 1 by 26, and that led to the fact that we had a perfect secret system, right, perfectly secret system. So and for every x which belongs to P and for every y belongs to C, there is a unique key. So that means that given an x and y, there is a unique key which takes x and maps it to y, right. So we have to establish this fact, that is, for every x and y you choose, or every tuple that you form with x and y, that is a given plain text and a given ciphertext, you have a unique value of key which defines this mapping. Okay. So we will try to establish this fact. Okay. So I will, although I will not prove, but you can easily understand that an equivalent definition of perfect secrecy will be PCY given x is equal to PCY. Okay. I leave it to you as an exercise. You can actually prove it by theorems of conditional probability. Okay. It's very simple, it's straightforward. So therefore, it says that the ciphertext probability of y is the same as the probability of y given x as the corresponding plain text. Okay. So thus, if perfectly secret, a scheme has to following the above 2 equations. Okay, and both of them are equivalent. If you can prove any one of them, the other one is proved equivalently, right. So we observe one fact. So we see that since PCY given x is equal to PCY, okay, that is, if you see this equation, it means that if you fix a value of x, for example, as a plain text, then your PCY given x is equal to PCY, right, and your PCY is greater than 0, because if that y, the occurrence of y, the probability of occurrence of y would have been 0, then y we wouldn't have kept in the ciphertext set, right. So that means for some ciphertext, at least for some plain text, at least we have that corresponding ciphertext, right. So immediately, which means that this leads to the fact that PCY given x is also greater than 0, right. So what I'm trying to say is that since PCY is greater than 0, and if we have a perfectly secured cipher, then PCY given x being equal to PCY, this is also greater than 0, right. So therefore, PCY given x is greater than 0. Okay. So which means that for every ciphertext there is a key k such that y is equal to ekx, right. So which means that for every ciphertext there is a key such that y is equal to ekx. Okay. So if you think in the terms of a diagram, okay, you could have understood that in the corresponding ciphertext set there is no single point which is not being mapped. Okay, there is not any isolated point which is not mapped to any plain text. Okay, so therefore your plain text comprises of what? x1, x2 and so on symbols, right. Your ciphertext also comprises of y1, y2 and so on symbols, right. So there is not a scenario where there is a ciphertext symbol, okay, say corresponding, consider any yi for example, which is not mapped to any plain text xi. Okay, do you understand that? So that means that for every ciphertext there is a key, there is one key at least which will take it to that x, be that any x. Okay. So what does it mean? It means that the size of the key set is obviously at least equal to the value size of the ciphertext. Okay, it can be greater than that also, but it is at least equal. So therefore, what I am trying to say is that for perfect secured ciphers, the size of the k or the cardinality of k is more than the cardinality of the ciphertext. Okay. Right. So you can understand again, again reiterating the fact, what I am trying to say is that for every ciphertext y, there is a key k which defines this mapping. Okay. So that means there has to be the number of the keys has to be at least equal to the numbers of the ciphertext, right? For every ciphertext symbol, you have a separate key which will define this mapping. So the number of keys is obviously equal to the size of the y. It can be more than that also, but at least equal, right? So therefore, the size of the key is greater than the size of the C. In our case, consider that the size of k and the size of C are the same. Okay. So thus there is no ciphertext. So therefore, now we can actually understand from here also that there is no ciphertext y for which there are two keys which take them to the same plain text. Why? Now because what is your size? How can you define your ciphertext set C? You can define your ciphertext set C by the set that you basically choose any plain text x and you transform that by ekx and you obtain the ciphertext, right? So basically that, suppose if I fix the value of x, I could have chosen all the possible values of keys and I would have obtained the entire ciphertext set, right? So that we know that if we say that, so this is your size of, so the cardinality of this set is the same as that of your ciphertext, right? Now if this is equal to the size of the value of the set of k, that is, it is the same as the size of k, it means that there are no two keys which are distinct like k1 and k2 such that ek1x is equal to ek2x, because in that case one cardinality would have been less, right? One of the sets cardinality would have been lesser than the cardinality of k, right? And what we have said is that if we assume that the size of k and the size of C are same, then essentially there is no two keys which are distinct which will take them to the same plain text. Okay. Thus there is exactly one key which defines the mapping from x and y. Okay. So therefore, this is the basic definition. So we see certain definitions crop out of the idea of a perfect secured cipher. Okay. So what are those definitions? One important point was that your a posteriori probability of your plain text matches with the a priori probability. Okay. The second definition was that, equivalent definition was that PCY given x was equal to PCY. So that is also the same thing, that the a priori probability of your ciphertext is the same as the a posteriori probability of your ciphertext. Okay. And the third important thing which we see is that if your size of plain text key and the ciphertext are the same, okay, then essentially for every plain text x and for every ciphertext y, for any ordered pair like this, there is a unique key which defines this mapping, right? So there are no two such keys like k1 and k2 which will take x, for example, as a plain text and will map it to the same ciphertext. Okay, ek1, where k1 is not equal to k2, we cannot have a scenario where ek1x is equal to ek2x, because if that be the case, then your size of ciphertext would have been lesser than that of the size of the key, right? But what we have said is the size of the ciphertext is equal to the size of the key, right? Is this part clear? So we will stop at this point and essentially break for a few minutes and come back with the definition of something which we call as the one-time pads. Okay.